Hi there, my name is Scott. I'm a professor of Earth Science at Southern Cross University, and this talk is a re-recording of a presentation that I gave to Port Macquarie Hastings Council staff and councillors on the 3rd of February 2022. And in this talk, what I'd like to do is to basically share with you the results of some research that a team and I did on Lake Cathie late last year. And we're basically looking at some of the longer term consequences of the really big iron floc event that happened in Lake Cathie and Lake Innes in 2020. So I'll begin with a quick overview of this talk, and I'm going to start by talking about the iron floc event itself. What on earth happened in Lake Cathie and Lake Innes back in 2020? Now, I'm aware that some of you might be watching this might be quite new to this and some of the chemistry, so I'm going to provide a very brief but essential context and some background information on acid sulfate soils and the behaviour of iron in the environment, because without that understanding, a lot of what I'll be saying is unlikely to make a lot of sense. Now then I'm going to talk about the brief. So this is basically what we did for Council and, importantly, why we did it. And then I'll discuss what we found, so the key findings and the implications, what we found, what we think it means, and I'll have a particular focus on some of the risks for water quality and amenity and under a series of topics. And then finally, I'll talk about what this tells us about the future and in terms of possible future scenarios and how they may play out. And last of all, I will touch on some of the uncertainties and key knowledge gaps that remain. So the iron floc event in Lake Cathie and Lake Innes in 2020 was really quite unprecedented, and it was extreme in both its scale and its scope. It was really certainly outside of any living memory. This aerial photograph that you're looking at here is looking at down at the perch hole in Lake Cathie sort of channel, and you can see all that orange and red coloured materials, basically kind of iron oxides or rust, deposited in the intertidal zone on the sandy sediments, and that's an extremely unusual thing to see. Now I've been working around acid sulfate soils for the last 30 years or so up and down the east coast of Australia, and I've really not seen anything quite like this in terms of mass mobilisation of iron. And really the only sites that you see that tend to look like this are acid sulfate soil drains and also sites that are impacted by acid mine drainage. So now time for a brief but essential background. So acid sulfate soils are characterised by containing some iron pyrite, and they form when the pyrite that's in them, which is often normally below the water table, when it's exposed to air, and it basically oxidizes, which is a bit like rusting. And acid sulfate soils are really quite common in coastal lowlands and wetlands. In fact, the map in the upper right hand side of this slide shows the red areas show locations with a high risk of acid sulfate soils in and around Lake Cathie and Lake Innes, and you can see they're pretty abundant in this area. Now when that pyrite is exposed to air, it reacts with the oxygen and it releases iron, and it also makes sulfuric acid, and it's actually one of the most acid producing reactions in nature. But a really important question is what happens to that iron once it's released? Well, iron in the environment tends to take two major forms. Now one of those is soluble and the other is largely insoluble. So the first one we call iron 2. It's represented in this box over here on the left, and this is readily soluble, so it's dissolved in water and therefore it's easily transported by water. The other we call iron 3, it's in this box on the right here, and this tends to form iron oxides or rust, and they are very, very insoluble. So they tend to form a flocculate and mineral precipitates when they are in contact with water. Now, one of the keys which determines which form the iron takes is the presence or absence of oxygen. Now, so below the water table, like in the groundwater, that tends to have fairly low oxygen, so this favours the formation of iron 2, which is soluble. Whereas above the water table, in surface waters, like a lake, you tend to have the presence of oxygen, so this favours the formation of iron 3, these insoluble iron oxides. Now, this is a gross simplification, but it should be sufficient. So this picture here of a wet sediment from a lake gives you a really good visual idea of how this can work when you go from a zone where there's low oxygen to a zone where there's high oxygen. So in this black part of the sediment that you can see in this photograph, there's really low oxygen. So the iron here is in the form of iron 2. So it's sort of dissolved in the pore water, in the spaces between sort of the grains in this black area. Now, as soon as this iron 2 sort of moves across into the area where there is oxygen, it reacts really quickly and forms these orange-coloured insoluble iron 3 oxides, like you can see in this picture. Now, a really important part of this reaction is that it can go both ways. It's reversible. So not only can iron 2 turn into iron 3 when it's exposed to oxygen, but if you take away the oxygen, iron 3 can turn back to iron 2. So the 2020 iron floc event in Lake Cathie and Lake Innes had a chain of causes, a long chain of causes. Now, some of those causes were natural and some of those were related to human activity. Now, in simple terms, the first thing is that there was a source of iron 2, and the source of that iron 2 was the extreme drought in 2019, and this caused the water levels in the lake and the water table around the edges of the lake to lower. And that caused the oxidation of pyrite in the soils, which released this huge store of iron. Now then there was reflooding, and the water levels came back up again for several months, and this meant that there was a whole bunch of dissolved iron 2 sitting in the pore water and the groundwater around the edges of the lake. Okay, so we've got a source of iron sitting there in the groundwater. Then you needed a force, to move that iron from the soil and groundwater into the lake. And that force was the entrance breach, itself. So the entrance breach in May 2020 caused a really fast drop in the lake levels. And you can see the change in the lake levels up here in this chart in the upper right-hand side. And so you had a situation where the lake suddenly became very low, whereas the groundwater on the edges of the lake was still high. So you have this difference in their head levels, and just through gravity you get seepage, and that seepage caused the groundwater that was rich in iron 2 to be transported into the lake. And when it hit the lake water had oxygen in it. It also tends to mostly have a neutral-ish pH. And so the iron 2 reacted really quick with oxygen and formed iron 3 floc, like you can see in this picture on the bottom right hand side. So what this basically caused was a mass translocation, or mass movement, if you like, of iron from deeper down in the sediments right to the surface, where it accumulated in the form of iron 3 floc on the bed of the lake. So this picture here gives you an idea of just how acute this was. This is up near the perch hole, looking down, and these are normally sort of white marine sands, and you can see there's just extensive iron oxides and floc, particularly on the margins of the island, right in that intertidal zone where the pore water seepage was happening. So, apart from degraded amenity and some locally degraded water quality and ecological consequences, all of this abundant iron 3 floc that's at the surface has a bunch of longer-term knock-on geochemical consequences, and this has the potential to alter the risk profile for the lake in the future. And this is what my team and I were investigating. Now, one of the first things is that all of this additional iron at the surface provides a potential basis for the formation of new pyrite right at the surface, and the formation also of this other thing we call AVS, which is kind of like pyrite's evil twin, if you like. It's even more reactive than pyrite, also produces acid. But the difference here is that because the iron's at the surface, this could potentially reform pyrite at the surface, and that would mean that in the future there's an enhanced sensitivity of the lake to droughts in the future, and lowering of water levels. Now, another potential issue is that the iron oxides themselves can act a bit like a chemical mop, where they encourage the accumulation of trace metals and nutrients like phosphate. They can tend to stick to the outside of the iron oxides. But these iron oxides can also be quite unstable. They're transient. and they're prone to change. Yeah, they can sometimes dissolve basically under the right conditions, and when that happens they can release the things that stick to them, like metals and phosphate, and so that potentially has implications for metal and nutrient cycling in the future. Now, there were also some additional unknowns. Last year we had no information about the persistence of iron 2 in the groundwater and pore waters on the edge of the lake. Was there any there still? If so, how much? Or had it been depleted in the previous floc event? We really didn't know. There was also no clarity about the abundance or the exact type of iron oxide minerals that had formed on the surface of the bed of the lake. So this brings me to the brief for Port Macquarie Hastings Council, and our mission was to see what all of this extra iron was doing to encourage the formation of both pyrite and AVS, especially near the surface where all this iron was being enriched. And it was also to evaluate and quantify the accumulation of this iron floc that was happening near the surface, see how much was there. And we also wanted to identify the iron minerals that were present and to see if indeed phosphate and trace metals were accumulating in those iron oxides and sticking to them. Now, we also did some additional work that wasn't in the brief, but we thought it was quite important, and that was looking at the pore water iron 2 concentrations as well as the acidity or pH in that water. And we also undertook an analysis of past breach events for the lake and had a look at how those breach events have affected lake water levels. So this was quite a small scoping study, so it was fairly limited in its spatial scale, and we looked at 11 different sites, and they were all situated in the Lake Cathie main channel zone. It's a really high use, high amenity area that's upstream from Ocean Dry Bridge and Kenwood Dry Bridge, as you can see in this photograph at the bottom of this slide. Now, this was designed to augment and complement the investigations by Soil Conservation Service, because they looked at acid sulfate soils right in the very bed of Lake Innes and Lake Cathie in the main lakes, and they found some really nasty materials in there. Now, the main sites that we selected that you can see in this map, we targeted areas where we thought they might have the greatest risk of reformation of pyrite. Basically, these little low energy sort of embayments and on the fringes and margins of the channel itself. Okay, so this brings me to the juicy bit, which is the findings and the implications. Now, in terms of RIS formation, RIS is just a fancy word for pyrite and AVS. The first thing we found is that there was fairly limited and low concentrations of AVS at the surface, remembering that AVS is basically pyrite's evil twin. Now, this is good. There was quite low concentrations of that when we looked. But there is indeed new pyrite that's forming near the surface, so in the upper 5 centimetres. And we're getting concentrations in excess of 1% by weight at some locations. And for sandy sediments, which these are, this is quite a high concentration. Now, you can see in this chart here, this shows pyrite concentrations at the top here in percentage terms in relation to the elevation in meters AHD. And you can see this pink shaded area here is near the surface, and this is basically where the new pyrite is reforming near the surface. Whereas in this green shaded zone down here, this is the older pyrite, that was already there prior to the drought. Now, just for reference here, this chart on the far right hand side, it's got the same elevation scale. This shows the water levels in the lake system during the drought in 2019. And what you can see is the lake water levels got right down into that green zone, where the older pyrite was. So indeed it was the drought that caused the oxidation of that pyrite, releasing the iron, which then led to the floc event. So what does all of this new pyrite that's reforming near the surface mean? Basically, it means that there's going to be increased sensitivity to future droughts. Because this pyrite is reforming in a zone where it's much more likely to be exposed to air. It's reforming right at the surface rather than deeper down. Now, there are nuances to this. The concentrations of pyrite that we saw in those surface sediments was pretty variable. Some sites were high, some sites were low. It's a natural environment. Variability is to be expected. Now this is another way of looking at it where I've averaged all of the data for those 11 sites and plotted the pyrite concentrations in relation to depth from the surface rather than in meters AHD. And so again, you can see this pink zone near the top. This is the upper 5 centimeters, and you can see this is where this new pyrite is reforming, and the green zone where the older pyrite is already there. And so this new pyrite is also forming right at the surface in this zone where the iron is enriched, like you can see on these two charts on the left here. It's enriched right at the surface. In fact, there's so much extra iron here that there's considerable potential for more pyrite to reform in the future. So it may actually get worse. And all of this boils down to the lake having enhanced drought sensitivity, enhanced risk of this surface pyrite reoxidizing, releasing iron, and releasing acidity. So what else did we find? Well, at the 11 sites, we also looked at the concentrations of iron 2 in the groundwater and the shallow pore waters, remembering that iron 2 is the soluble form. Now, to be honest, there was actually quite a lot, and we found this quite surprising. And this chart in the middle here, down the bottom, shows the concentrations of iron 2 on the bottom axis, on the x-axis, in relation to depth in meters AHD. And you can see the concentrations get pretty high, up to almost 800 milligrams per litre, which is really quite a lot. And this is in groundwater on the sediments, on the edges of the lake, within the intertidal zone range. Now, importantly, some of these pore waters and groundwaters were still quite acidic, which you can see in this chart over here on the far right, which shows a pH scale from 3 to 7 on the bottom. Some had a pH down around the 3 to 4 range, whereas some were up around the 7 range. And what this together really tells us is that the shallow groundwater on the edges of the lake is really yet to recover fully from the effects of the drought. Some of it is still quite acidic, and there's certainly still plenty of dissolved iron. So what does this mean? Well, persistent high concentrations of iron 2 means that these intertidal zone waters are effectively primed. Yeah, the system is basically sort of loaded, if you like, and in immediate risk of another iron floc event if there is a force, to move that iron 2 rich water into the lake again, i.e. if there is a rapid drawdown in lake water levels, such as you see during an entrance breaching event. Now, we didn't really expect this, to be honest. We expected the iron 2 concentrations to be largely depleted from the first couple of floc episodes, but that wasn't the case. So we also had a look at the iron floc itself, right at the sort of surface 1 centimetre or so of sediment. And indeed, there is a lot of iron oxide accumulated there. You can see concentrations in these two charts on the right, just using different scales. And it gets up to nearly 20% or so by weight. Yeah? So you could almost mine it. That's a joke, by the way. You couldn't, but it's pretty high. 20% is very high for iron concentrations. Now this is happening right in the intertidal zone. And you can see that's where the peak in the iron concentrations is. And this is because every time you get a little bit of, every time there's an ebb tide, you get a little bit of pore water seepage happening. And that causes the iron to sort of accumulate right in that intertidal zone. So there's a lot of iron forming there in the surface sediments. It's in the form of iron oxide minerals. But there are lots of different types of iron oxide minerals. And identifying the exact type of mineral is important because that can tell you a lot about the environmental conditions under which they formed, but also how they're likely to behave in the future. Now, in very simple terms, and I'm not going to go into the data because it's pretty complicated, we basically looked at these iron oxides using X-ray techniques, and we found a couple of things that are pretty important. First of all, we found that these iron oxides, there was quite a few different types, were very poorly crystalline. So that means that the mineral structure in them is not very strong and it's not very well developed. And poorly crystalline iron oxides have a couple of characteristics that are really important in terms of their environmental behaviour. First of all, they tend to have a really high surface area because they're very small as well. They tend to be nanoparticles. So they can be really good at mopping up trace metals and phosphate from the environment because they've got a huge sort of surface area with these lots of small particles. Now, secondly, they are what we call metastable, which is basically a fancy way of saying they're unstable. Yep. So they're quite prone to change and prone to potentially dissolving, especially if the oxygen levels go down or change, or if the acidity levels change and it becomes more acidic. And so if they dissolve, this can cause them to release the metals and the phosphate that's sort of stuck to them, to potentially release that into the surrounding water. So the next important question is, are these iron oxides actually mopping up phosphate and trace metals? The shorter answer is, you betcha. Yeah, they certainly are. Now, in most cases, they're not exceeding sediment quality threshold sort of guideline values, but compared to natural background levels in the lake, it's actually quite a lot, often in excess of 10 times. Now, this set of charts here on the right shows the concentrations of iron. These are from samples collected from 1 centimetre deep, so right near the surface. Concentrations of iron are on the bottom axis of all of these charts. And on the side, we have concentrations of phosphate, arsenic, chromium, copper, manganese, nickel, lead, and zinc. And the red triangle that is in each of these charts here is basically a local reference point for marine sand. And this was collected just on the eastern side of Ocean Drive Bridge. And what you can see in all of these charts is that there's a strong positive correlation, a strong relationship. So basically, when you get more iron, you have more trace metals and more phosphate. Now, whilst ever the phosphate and the trace metals stays bound to and associated with the iron oxides, it's kind of not such an issue. It's kind of locked up a bit. But because these iron oxides are unstable, there is a risk that some of this may be released if environmental conditions change. And environmental conditions do often change in icols like Lake Cathie. So lastly, in terms of findings, we also had a look at the effect of past entrance breaching events on lake water levels. We looked at 8 different events over the last decade, from 2011 to 2021, and you can see those 8 events labelled on this chart here, which shows lake water levels in blue versus time. Now, when you take each of these 8 events and you plot them on the same time axis, with days after entrance breach, like in these 2 charts, what we clearly see here is that while each of the events is unique, they all behave in a very similar way. And basically, average lake water levels tend to drop by about 1 metre to 1.5 metres within about 2 to 4 days after the entrance breach, depending on the event. Now, this is important because what it means is that entrance breaching, dropping those lake levels fast, will tend to trigger seepage of pore water from the intertidal zone on the fringes and margins of the lake. And we now know that that intertidal zone has a bunch of iron 2 dissolved in it. So when you bring all of this together, what might it mean for the future? Now, I think certainly it means that the main channel of the icol in Lake Cathie has a heightened sensitivity, and is at greater risk of degraded water quality and degraded amenity. And it's at risk right now, because any entrance breach that happens now will encourage and trigger some of that iron 2 that's in the pore waters to seep into the lake and potentially trigger a further iron 3 floc event. Now, one would hope that it's not going to be as bad as the first and the second ones that happened in 2020, but that's just sort of a hope. We don't really know enough to be able to say that. Maybe the iron 2 concentrations are a lot less now than what they were during the first event when that happened, but we don't really know because we don't have any data from back then. All we know is that the iron 2 concentrations are actually quite high at the moment. Now, there's also a risk into the future, because any future droughts that cause low lake levels will risk causing oxidation of this new shallow pyrite that's formed at the surface, which will release new acidity, and at least locally, and also release iron. Now, because this pyrite is reforming at the surface, this risk is clearly heightened compared to what it was before. And I probably don't need to point out that we're also moving into an era of climate change where we're likely to get enhanced climate extremes, including things like droughts down the track. Now, additionally, in the future, there is some risk that any large changes in pH, so if it gets more acidic, or if there's a change in the oxygen status and what we call an upward redox boundary migration, basically sort of low oxygen in those surface sediments of the lake, this could destabilize those iron oxides that are there and cause them to release some of their phosphate and trace metals. Now, I think one of the really important concepts to get across here is that the lake system is really in a new sort of biogeochemical state. It's not like what it was in the 1970s. You've essentially had this really large amount of iron, that had been slowly stored away in the sort of in the form of pyrite in those deeper sediments, and it had been slowly stored over hundreds, thousands of years, and now it has suddenly been released and transported into the surface layers. And so this is a kind of what we call a hysteresis, where the path back to what it was isn't the same as the path forward. It's really sort of flipped into a new state, and as a result, we're likely to see persistent and pretty dynamic cycling of iron within the intertidal zone sediments and pore waters in Lake Cathie and Lake Innes over the immediate future, perhaps for quite a few years, and it will tend to sort of cycle and shift around, if you like, in response to changes in water levels. So there's basically going to be this enhanced sort of sensitivity, if you like, to climate oscillations. Now, it may also be that there's a gradual decline in the intensity of these surface oxides. They might sort of gradually sort of back off over time, and this could be due to a number of different things happening, including downward sort of reworking of the iron oxides. So this is like through bioturbating organisms or burrowing critters that live in the sediments, taking the iron further down, as well as a bit of dilution and flushing, which would be pretty slow, but it will slowly happen. Also, potentially changing it through transforming the iron oxides to more crystalline minerals, which can also happen over time, gradually. And finally, importantly, potentially locking up this soluble iron 2 that's in the groundwater as newly formed minerals, like pyrite, actually. But that process takes time. So I guess in terms of a conclusion and what are some of our kind of key uncertainties and knowledge gaps, we certainly know a good deal more than what we did back in 2020 when this first happened. But there's still a lot of unknowns. We only really examined about 11 sites, and variability is often quite high in the natural environment. So there's a lot more that could be done to better constrain the nature of the risks. For example, we don't really have a proper full budget for this newly formed pyrite in the main channel zone. How abundant really is it? We only did 11 sites. What's the true spatial variability? Are there any hotspots? And importantly, what's the future trajectory? And how will that future trajectory relate to water quality risks? Now, another key question, I think, is how long will it be until this pore water iron 2 is kind of rebound up in solid phase minerals over time, because it will gradually over time, if it's sort of under stable conditions, it will tend to form new minerals like pyrite, and that'll remove the iron 2 from the pore water. The practical sort of dimension to this question is basically how long will it be till we can have an entrance breach that no longer poses a risk of recreating another iron floc event. Now, unfortunately, we don't know the answer to that question as yet, and that would take some further work. And another uncertainty relates to the potential behaviour of this iron floc associated phosphate and trace metals during sort of future changes in oxygen status or redox boundary migration or changes in pH. What might this mean for water quality? Now, it's possible to answer that, but that would also take some targeted sort of work and research. So, in summary, I think it's pretty fair to say that Port Macquarie Hastings Council and the community have kind of inherited a bit of a pickle, and it's going to take some pretty careful and well-considered science-based management to really try to minimise the risks to water quality in the lake system in the future. That's about a wrap. Thank you very much for your time and attention. I hope it was useful. Cheers.